There are certain times when we want the registers in a big digital system to be all reset to a very specific state. Say that you want all the registers and flip-flops in a system to be reset to 0 with the press up of a push button, or maybe you want all of them to be set to 1. So in this section, I'll introduce this particular functionality, and more interestingly, I'll talk about how we can do it in terms of time. We can do it synchronously or asynchronously, and you can have all sorts of combination of these. So you can have a synchronous set, asynchronous reset, or a synchronous set, asynchronous set, and so forth. You can have all sorts of 4 combinations of these. So how can we do this? Of course, we can go ahead and look at the structure of a flip-flop. So in here, I'm showing you just a simple D flip-flops that is composed of a couple of latches. This is the D latch, this is another D latch. These are the master-slave configuration. And what we did is we added some sort of wiring here in blue and wiring here in blue. And these particular functionality in here, this will make it 1, this will make it clear to 0. Regardless of what we do here on D, and sometimes it's regardless of what we do on the clock. Of course, we can go ahead and build this structurally and use hierarchical design to build the whole system. But in here, what I want to do is I want to focus on how we can describe this particular functionality behaviorally, because it's more interesting and this is what most commonly is used nowadays. So in this video, I'll just go through this particular diagram in here and I'm going to describe it. I'm going to describe all sorts of ways that we can do or things that we can do with that. So what you see is just a normal edge triggered D flip-flop, and specifically it's actually triggered by a negative edge of the clock. And what I'm showing you in here, of course it has the D, the Q, and the Q bar, but I'm showing you more interesting inputs, and these interesting inputs are the ones here and the ones here. So the first one we're going to actually tackle is this one, which is a reset. So if you put a 0 at this input, this is what this circle means. It's active low. You're going to set that particular value for this flip-flop to 0 regardless of what's happening at the D. So the signal is usually called a reset. Sometimes you're going to see all sorts of combinations of names. I'm writing them all in here. So you can see it reset, or sometimes it's called clear. The underscore B or underscore N represent that actually active low. So the underscore B stands for bar. So sometimes you might see it reset bar, but of course, because we are talking about computers, we don't have a bar. So we say underscore B. Underscore N is just basically similar to the negative edge of the clock. It's just like negative. So sometimes you see all sorts of combinations. I usually tend to use reset N, but I use these interchangeably. So if you see me doing this anyway, like you can replace it with a different one. The same goes with this particular input, but this particular input, instead of setting that flip-flops to 0, it sets it to a value of 1. Okay. And of course, the name is usually set or preset. And again, the underscore B or underscore N represent it's actually active low. If it is active high, you just don't not use the underscore at all. You just say set, preset, or reset and clear, and that's it. So let's go to Vivado and try to write some code to describe this set and reset functionality for a single D flip-flop. So I went ahead and I created a module. I called it D flip-flop, and I gave it an input clock and an input D, and I called it reset N. It's active low, and I said let's start with an asynchronous version. So the reset can be synchronously or asynchronously, and I'll talk about the difference in a minute. And of course, I give it an output. You can of course give it the Q bar if you choose to, but for now we're just going to focus on that. All right, so how do we write this? Of course, we have written something very, very similar when we opened an always statement. Then we said, okay, at the negative edge of the clock, all I want is begin and an end, and we wanted the Q to be equal to D, of course, because now we know the difference between blocking and non-blocking assignment. I can technically use this. However, this doesn't follow the style of separating the inputs and the outputs or the registers and the combination circuits separately. So in here, I'm just going to make sure that I follow that style. So I'm going to say reg, and that particular register will be reg and Q next. Okay, and I'll be using Q reg and Q next. Q next would be the next value. Q reg is the current value. And that's how I'm going to use it now. So of course we can usually, if I'm separating the registers and the next state, I'll say, well, Q reg should be just equal to the Q next, the next value. And I'll figure out what the next value in here with a different always statement. And in the different always statement, I'll figure out what the input should be, begin and an end. I just want the Q next to be, well, it should be D. So that sensitivity list should be at the D. And that's pretty much it. That describes the normal D flip-flop that we have seen. Again, you can see that the code is a lot more verbose, but it's a lot more easy to follow. So I know that the next value would be based on D, and that next value will only be updated based on the negative edge of the clock. So now we get to actually adding a reset. So the reset can be added anywhere we want. Okay, we can add it in here or we can add it in here, but the meaning will be dramatically different. So we're going to start, because I have this comment in here saying asynchronous, we're going to start by asynchronous. What's an asynchronous? Well, and the functionality of this reset is to make sure the flip-flop is actually zeroed out regardless of the D. And frankly speaking, when we say asynchronous, that means it's also regardless of the clock. I do not care where the clock value is. The minute this gets asserted, which means you set it to 0, I want the flip-flop to be 0. So what I need to do is I need to go to this particular sensitivity list, and I'm going to say, well, I also need the reset N. But because we have already used the negative edge of the clock, whenever you use an edge in one of the signals in the sensitivity list of an always, you're going to have to use it in all of them. So we're going to have to say the negative edge, because I'm looking for whenever it is actually going to 0. So I'm looking for 1 to 0, which is a negative edge. And what I'm going to say is the following. I'm going to say, well, if it happened that the reset N is actually not asserted, basically it's 0, so all I have to say it's not in here, or technically speaking I should do it this way because it's a logical question. What I need to do is, let me just do this here. What I need to do is I need to make sure that QReg is actually equal to 0. Specifically, it's going to be 1 bit 0, or 1 bit binary 0. Other than that, I'll make sure that it's actually taking the value X. So again, what I'm doing in here is I added this in the sensitivity list. This tells me I don't care what clock is. The minute you actually do the reset, it's asynchronous. You will actually set it to 0, regardless of the clock, whether it's active edge, non-active edge, positive, negative, whatever it is. The minute it goes to 0, we're going to reset it to 0, and that's what we call an asynchronous reset. All right. In here, I don't have to change anything. The next value will be always D. Okay. And sometimes I use it, sometimes I don't use that next value. So let's add another input, and let's call it input clear, and I'm going to call it B just for the sake of argument. Of course I can use D. Let's use D. Okay, and this time I'm going to say that this is the synchronous reset, or the synchronous clear. I'm just calling it clear to differentiate between them. Okay, the clear and reset doesn't matter. Like sometimes you might look at the code and reset would be synchronous and clear would be asynchronous. Sometimes one of them appear and not the other. But anyway, the functionality of the clear is to make sure that the D flip-flop is actually reset to 0, but because I need it synchronously, it will care about the clock. So because it will care about the clock, I need to make sure that it only gets updated with the clock. So what I really need to do is I need to make sure that the Q next is the one updated, and the next edge clock that comes in, Q next would be at that point to 0. So what I have to do is I have to actually modify my code in here, and I'm going to say, well, if it is not clear N, okay, I will say Q next, not the Q reg, but the Q next should be equal to 1 bit 0. And in here, we can say that else the Q next would be D. And for the sake of completion, you can actually just say, okay, I'm just going to make sure, remember this is a combination of circuit in here. That's why we're using blocking assignment. For the sake of completion, usually I say, well, I want to make sure Q next is assigned some sort of a value. So I'm going to make sure that at least it takes the current value by default, just in case something happened with this if statement and it doesn't take it. That's just a coding style. You can do the same exact thing in here if you want to. You can say, well, QReg equals QReg. Basically, do not change it. I mean, this is meaningless, but you can do that for sure. All right, so now what I have just created is I have created a single flip-flop that has a couple of reset. One is actually asynchronous and the other one is synchronous. However, I'm still missing, because I use the QReg and the QNext, I still need to make sure what the output is, and the output here is Q. So I'll have to make sure that this is assigned Q equals, I believe it should be QReg, the current value of the register, and now I am done. All right, so we wrote that flip-flop, but I believe I forgot to include the clear N in here. That should be included in the sensitivity list, because I'm depending on its value to actually do something. So if clear N actually changes, I need that always statement to get executed or to get invoked. So now this is done. We can take a look at the elaborate design just to see what will happen. And what I got exactly what I expected, which is a flip-flop in here, and that flip-flop has its reset, which is an asynchronous input connected to this extra reset in here. However, the synchronous reset is actually, which is clear N. Okay, it's connected to this multiplexer, which either gives me a 0 or the default value of D, and it's actually passing through D. The more important thing, it's actually going through D, so it's synchronous. It's actually based on the clock itself. So let's run, I wrote a test bench just to see the differences and how the reset and the clear N actually operate. Remember, reset is asynchronous, so no matter what, whenever I actually set it to 0, I should expect the output to be 0. So let's see that. So that's the reset. We can definitely change the color in here and make it that. So you can see that here, what I did is I said, okay, the reset is actually 0, the output got to 0. And here it stayed at 0, and then the next active edge of the clock, which is a negative edge of the clock, which is not this one, but actually this one, it sampled the D, and the D is 1. That's why the output stayed at 0. Again, we're going to take a look at this reset in here, and I'm going to see that it actually got reset in here. Regardless of what's happening to the clock, there's no active edge in here. The output got to 0. And it stays at 0 as long as this is asserted in here, and then the next active edge of the clock, which is a negative edge in here, D got sampled, which is 1, and the output is 1 in here. So now let's take a look at the clear N, and the clear N, let's do that in gold, for example, just to change the color a little bit. So clear N is a synchronous one, and you can see that at some point in here outside the clock, I made it at 0, but it didn't affect the output whatsoever because it's a synchronous one. But in here, what happens is I made sure that it actually stays at 0 within an active edge. So an active edge comes in, and this is at 0, and you see that the output got reset to 0, even though that D is actually still at 1. And the next time that D goes to 1 is actually for the next clock cycle, when it actually gets out here and it samples D, and D is, or the output is 1. And that's how we actually design synchronous or asynchronous reset. The set is very similar. So a D flip-flop with the set or reset can be composed in a very similar fashion. So for example, let me just copy and paste that code in here. So we can do this here. We can do that. And I believe I have included some sort of signals, so I'm gonna have to delete all of this here. So in this here, what I did is I decided, let's make sure that just the reset, the asynchronous reset is there. I'm not gonna care about the synchronous clear. So we're gonna just do this one here and this one here, and that's basically, we can do that. What I did is I added another input, and that's set in. And set in is actually the one that should make it equal 1. So if I want it to be asynchronous, all I have to do is just do the same exact thing we did in here. Just add it, make sure that I add another case statement that tests for it too. Of course, you're gonna have to figure out whether it's if or the if else and so forth. But what I'm going to do is I'm just going to make it as an asynchronous input. So I'm going to say, okay, if set N is actually asserted, which means it's at 0, so I have to do that. Okay, I will say that the Q next should be equal to 1 bit 1. I'm actually setting it to 1. Other than that, which is else in here, I can say that Q next should be just a D. And for the sake of completion, we can just give Q next a default value, which is just the current value of the register. Okay. And again, we're going to have to modify that always statement to say, well, I'm depending on the value of set now. So I'm just going to do this here. And now I have a set and a reset. So I have an asynchronous reset because it's actually in here. And I have an asynchronous set because it's only happening through the D or the next here. So it's only happening when the clock actually happens. That's why it's synchronous. It's actually with time. So in here I have ran some sort of a test bench that actually has the asynchronous reset and the synchronous set. So as we expect, the asynchronous reset, no matter what, whenever it's at 0, you're going to see that the output set to 0. This will be at 0. Okay, now more interestingly is the set. Let's make it in a different color so that we can see it in here. So maybe something else, maybe aqua or something like that. Okay, so we say the set. So the set, I actually did it here. I set it to 0, but because the clock was not active, the Q stays at 0. Of course, I made it 0 in here at some point. Okay, I believe, how did I do that? Yes, I did that in here. So in here, it actually comes in here, it samples to 0, and that's it. Of course, I wanted the set, but because it's a synchronous one, it only does it if the clock or the active edge comes in. So we're going to see the next one in here. This isn't the active edge, so I'm going to have to move it. Well, I need to modify my test bench a little bit so that it's actually shifted a little bit, maybe a little bit further. So let me just do this and come back. So I went ahead and modified my test bench a little bit. So this one here is still outside the active edge of the clock, but this one here now, I made it at 0 and the active edge of the clock, which is a negative in here. And as you might expect, the output got into 1, regardless that the D is actually at 0. So it set it to 1 exactly when the active edge of the clock happened.